Router single-arm routing configuration. First, let's take a look at the objectives of the experiment. To understand the configuration method of single-arm routing and achieve mutual communication between different VLANs using single-arm routing. The background of the experiment is as follows. A certain company has two main departments: the technology department and the sales department, located in different offices. To enhance security and facilitate management, the hosts in both departments have been divided into VLANs, with the technology department and sales department placed in different VLANs. Due to business requirements, the hosts in the sales department and the technology department need to access each other's resources. To facilitate this, the switches of both departments are connected through a router. The technical principle behind single-arm routing is to achieve communication between VLANs. A Layer 3 network device, such as a router, only needs one Ethernet interface with multiple sub-interfaces to serve as the gateway for all VLANs and forward data between different VLANs. The experimental steps are as follows. 1. Use Packet Tracer software to create a new topology structure. 2. Configure VLAN 2 and VLAN 3 on the Layer 2 switch, and assign ports 2 and 3 to VLAN 2 and VLAN 3, respectively. When the switch is configured with two VLANs, logically, it becomes two separate networks, and broadcasts are isolated. Communication between the two VLANs requires a router. If connecting to the router through a physical port, there must be two sub-interfaces, each corresponding to one VLAN. Additionally, the Fast Ethernet 1.0.1 port of the switch connected to the router should be set to trunk mode, because this interface needs to handle data packets from both VLANs, and must be able to recognize data packets from both VLANs. The challenge lies in how to configure this interface on the switch. The experimental steps are as follows. After completing the configurations, verify the settings to ensure that VLAN and trunk information are correctly displayed. Set the default gateway of the computers to the IP addresses of the router's sub-interfaces. Configure the sub-interfaces on the router and enable routing on the physical interface. Ensure that the default encapsulation is set to .1q protocol. Configure IP addresses for the router's sub-interfaces. These IP addresses are similar to the SVI addresses on the Layer 3 switch. Finally, check the equipment used in the experiment. First, there are two PCS, one 2811 router, and one 2960 Layer 2 switch. In the experimental topology, the two PCS are connected to the Layer 2 switch. The Layer 2 switch is configured with a trunk that connects to the router, allowing VLAN information to be transmitted to the router. Now, let's see how to use the Packet Tracer simulation software to implement the router's single-arm routing. According to the experimental requirements, we create the experimental topology by selecting one 2811 router, one 2960 Layer 2 switch, and two PCS. We set the names of the devices and connect PC1 to the Layer 2 switch port 2, and PC2 to the Layer 2 switch port 3. The Layer 2 switch port 1 is connected to the router's interface FA0, 0th. Next, we will configure the IP addresses for the two PCS. PC1 and PC2 will have IP addresses belonging to different subnets. We will test the connectivity between PC1 and PC2 by pinging PC2 from PC1. However, we observe that they cannot communicate directly due to being on different subnets. To address this issue, we will perform the following configuration on the Layer 2 switch. We will set the two ports connecting to different subnets as separate VLANs. Firstly, we enter the global configuration mode on the Layer 2 switch and create VLAN 2 and VLAN 3. Then, we assign port 2, which connects to PC1, to VLAN 2, and port 3, which connects to PC2, to VLAN 3. Finally, we set the port connecting to the router as a trunk port. Next, we will proceed with the configuration on the router. We enter the global configuration mode on the router and enable interface F0, 0th. Then, we access the first subinterface of router, module 0, set the encapsulation protocol to .1q, and allow traffic from VLAN 2 to pass through. We assign the IP address of this subinterface as the default gateway for VLAN 2. Similarly, we access the second subinterface of router, module 0, set the encapsulation protocol to .1q, and allow traffic from VLAN 3 to pass through. We assign the IP address of this subinterface as the default gateway for VLAN 3. We also check the routing table on the router to ensure that there are paths to reach VLAN 2 and VLAN 3. Now, we will perform a connectivity test by pinging PC2 from PC1. We observe that they can communicate successfully. Through this experiment, we confirm that communication between different VLANs must go through the router. When there is only one physical link connecting to the router, we can create subinterfaces to act as the gateways for different VLANs, thereby achieving communication between different VLANs.